For most of modern science, a crystal meant one thing, a pattern that repeats, like wallpaper, like tiles, like a code you can copy forever. And that rule felt unbreakable, because it wasn't just a habit, it was built into the definition of crystallography. Then in 1982, a materials scientist named Dan Shechtman looked at an alloy under an electron microscope and saw a diffraction pattern that basically said, "This is ordered, but it does not repeat." Worse, he saw a symmetry that classical crystallography said a real crystal could not have, 5-fold, 10-fold patterns that should be forbidden in a repeating lattice. For a while, many scientists assumed it had to be an error, twinning, contamination, instrument artifact, anything except a new kind of solid. But it wasn't an artifact. It was a new category of matter, quasicrystals. And here's where the title becomes true in a careful, scientific way. Quasicrystals exist in 3D space, but the cleanest way to describe their order uses higher dimensional mathematics, as if the structure we see is a projection of a pattern that lives in more dimensions than our everyday world. Not magic, not another universe. A real material, whose order is easiest to understand using a dimension you can't physically build. And once you understand that, you'll see why quasicrystals aren't just a scientific curiosity. They're becoming a tool in advanced alloys, coatings, and manufacturing, especially where friction, wear, and microstructure control matter. Quasicrystals aren't famous because they're weird. They're famous because they're useful. When you change how atoms can arrange themselves, you change the menu of properties engineers can access. Hardness, where resistance, friction behavior, thermal transport, and how an alloy solidifies during manufacturing. And right now, manufacturing is pushing into regimes where microstructure is everything, especially additive manufacturing. In metal 3D printing, cracking, hot tearing, and grain control can decide whether a high-strength alloy is printable or impossible. Quasicrystal-related phases and quasicrystal-inspired microstructures are showing up as a new lever, not necessarily as a bulk quasicrystal part, but as a way to influence grain formation, strengthen surfaces, and tune wear and friction. So the stakes aren't we found a material from another dimension. The stakes are we discovered a new kind of atomic order, and it opened pathways to engineer materials in ways traditional crystals don't allow. But to understand why, we need the origin story, because this wasn't discovered by searching for exotic symmetry. It was discovered by accident and stubbornness. In 1982, Dan Shechtman was studying an aluminum-based alloy, famously including aluminum and manganese systems, when he saw something that didn't fit the rules. In electron diffraction, crystals produce patterns of spots that reflect their internal order. A repeating crystal lattice gives you repeating symmetry constraints. But Shechtman observed a diffraction pattern with a kind of symmetry that the old rulebook said couldn't happen for a periodic crystal. His notes reportedly included the essence of the shock. This can't be right. And yet it's what the material is showing. The reaction from parts of the community was harsh, not because scientists were villains, but because the claim threatened the foundational classification system. And some very influential voices strongly rejected it. Most famously Linus Pauling, who argued for conventional explanations and criticized the quasicrystal interpretation. But over time, as evidence accumulated and other groups observed similar structures, the conclusion solidified. This wasn't a repeating crystal pretending to be strange. It was a new kind of order, long-range order without periodicity. That discovery reshaped crystallography so deeply that Shechtman ultimately received the Nobel Prize in Chemistry in 2011. Now let's unpack what that phrase actually means, because it's the core of the dimension story. Here's the cleanest way to understand quasicrystals. A normal crystal is ordered and repeating. If you shift it by the right distance, it matches itself perfectly. That's periodicity. A quasicrystal is also ordered. There is structure, rules, and long-range pattern, but it does not repeat in a simple unit cell. So you get something that feels contradictory. Ordered enough to produce sharp diffraction spots, not a glass, but non-repeating enough to break the old crystals must be periodic assumption. This is where people get confused by the Pentagon story. It's not that pentagons can't tile a floor. In every sense, many pentagons can tile the plane. The real point is about forbidden rotational symmetries in periodic crystals. Classical crystallography allowed rotational symmetries like 2, 3, 4, and 6-fold for periodic lattices. 5-fold symmetry doesn't fit periodic repetition in the same way. Quasicrystals can show 5-fold or 10-fold symmetry because they are not constrained by periodicity. So the impossible isn't geometry in your living room. It's the old rule of repeating atomic lattices. Now the question becomes, if it's not repeating, why is it still order enough to be a solid with defined structure? That's where higher dimensional math comes in. Quasicrystals don't literally exist in a sixth spatial dimension, but their order can be described as if it comes from a higher dimensional periodic pattern, then projected into 3D. Here's the intuition. Sometimes a pattern that looks complex and non-repeating in 3D becomes simple and repeating if you allow extra coordinates. So researchers model quasicrystal order using a higher dimensional lattice, often described in 5D or 6D, depending on symmetry, then mathematically projected down into 3D space. In other words, the material is fully real and fully 3D. But the cleanest description of its symmetry behaves like a shadow of a higher dimensional periodic structure. That's the only dimension claim you need, and it's genuinely mind-bending without being mystical. And this mathematical structure isn't trivia, because unusual order changes how defects move, how surfaces interact, and how friction and wear behave. Which brings us to the engineering. What does quasicrystal order do to material properties? Quasicrystals often show unusual combinations of properties, especially compared to typical metals. Many quasicrystals and quasicrystal-containing alloys are known for high hardness, low friction, and wear behavior in certain contexts corrosion resistance in some systems and lower electrical conductivity than typical metals, depending on composition and structure. The why is not one simple trick. It's a combination of atomic order that isn't periodic different electron scattering behavior compared to ordinary metals and microstructural effects in real alloys, because many uses involve quasicrystal phases inside a more conventional matrix. Also important, quasicrystals can be brittle in bulk form. That's why many applications use them as coatings, particles, or reinforcing phases rather than as large structural blocks. So the practical engineering approach is often use the quasicrystal where its surface or microstructural benefits matter, hardness where friction, without demanding behave like a ductile steel beam. Now add modern manufacturing to that, and the story gets even more relevant. Because in additive manufacturing, microstructure control could be the difference between printable and cracks instantly. Shechtman's story is famous because it's a real example of how science handles claims that don't fit the framework. A discovery challenges a definition. The community tries to explain it away. Independent evidence accumulates. The definition changes. That last step matters. Quasicrystals didn't just win an argument. They forced crystallography to expand what counts as a crystal. And the conflict with Pauling has become legendary because it shows something uncomfortable. Even brilliant scientists can be wrong when the framework is outdated. Shechtman's eventual Nobel Prize wasn't just a personal vindication. It was a sign that the scientific system can absorb shock, rewrite its rules, and move forward. And once quasicrystals were accepted as real, research exploded, not just in theory, but in practical metallurgy and materials engineering. Which brings us to the part people care about today. Where are quasicrystals actually used? Quasicrystals show up in the real world in a few grounded ways. Wear-resistant and low-friction surfaces. Quasicrystal-containing coatings and composites have been studied and used for their surface properties, especially where sliding wear matters. Alloy microstructure control. Some research explores quasicrystal-related phases as particles that influence how grains form during solidification. That's relevant to casting and potentially to additive manufacturing, where grain refinement and hot tear resistance are major challenges. Thermal and corrosion behavior in specific systems. Depending on composition, quasicrystal phases can contribute useful corrosion resistance and thermal characteristics. What's important? The most realistic near-term impact is not a whole airplane made of quasicrystals. It's quasicrystals as a microstructural tool, an ingredient that helps an alloy behave better, print better, or last longer. That's the Future Forge theme. Breakthroughs don't always enter society as a headline product. Sometimes they enter as a phase in an alloy that quietly changes what manufacturing can do. But there are limits, and they matter. Quasicrystals are powerful scientifically, but they're not a universal solution. Key limits: brittleness and bulk. Many quasicrystals can fracture rather than deform like ductile metals. Manufacturing control. Creating and maintaining the desired phases and microstructures can be sensitive to composition and processing conditions. Scaling. Producing consistent quasicrystal-related effects across industrial-scale manufacturing can be challenging and cost-sensitive. There's also a communication risk. The higher dimensional story can attract hype. The honest stance is, higher dimensional math is a tool for describing symmetry and order, not evidence that the material literally lives in another universe. The real controversy isn't do quasicrystals exist? That's settled. The controversy is how quickly and broadly they can be engineered into practical manufacturing flows, and where they outperform cheaper alternatives. And that leads to the breakthrough angle. What changed between weird discovery and engineering tool? The big shift wasn't just accepting quasicrystals. It was learning how to use them in controlled ways. As phases and aloysis particlesis coatinxes microstructure modifiers. This is where materials science becomes manufacturing science. It's one thing to discover a new form of order. It's another to make it reproducible, stable, and beneficial inside real industrial materials. The win isn't a single miracle property. The win is a new knob engineers can turn, controlling microstructure and surface behavior using atomic order that doesn't fit the old periodic rulebook. And that's why quasicrystals are still showing up in research tied to advanced manufacturing. Because once you expand a set of possible microstructures, you expand what alloys can do. Now let's project forward, carefully. In the next 5 years, expect quasicrystals to keep expanding as coatings and surface solutions microstructural phases, in advanced alloys and research tools for understanding non-periodic order. In 10 years, the biggest impact may be in manufacturing integration. Better process control, better models, and clearer when you use it rules that let quasicrystal-related phases move from niche to standard tool in selected applications. In 20 years, the most interesting effect may not be a single product. It may be conceptual. Quasicrystals have already taught materials science that order is bigger than repetition. As we design more extreme materials, metamaterials, topological systems, nano-architected solids, that lesson matters. Because engineering increasingly means designing structures whose behavior comes from geometry and symmetry, not just chemistry. Quasicrystals connect to the wider future forge world perfectly. Symmetry and microstructure control, phase engineering and alloys, advanced coatings, additive manufacturing limitation, sand the broader idea that materials are increasingly designed in spaces bigger than what you can see. Parameter spaces, topology, and structure property maps. They're a reminder that the most powerful materials breakthroughs often start as a measurement anomaly, then become a new design language. If you're an engineer or student, quasicrystals are a mindset upgrade. They teach you not to confuse the rules we use with the rules that exist. The old definition of a crystal wasn't wrong. It was incomplete. And that's a useful lesson for every emerging technology you'll touch. Additive manufacturing, smart materials, nanotech, metamaterials. The first model is rarely the final model. So here's the question. If you could add one new knob to material science, one new type of order, one new controllable symmetry, what would you want to do? Quasicrystals don't prove that reality has loopholes. They prove something better. Reality is deeper than our first definitions. A material can be ordered without repeating. A solid can follow rules that don't look like the rules we teach at first. And higher dimensional math can describe a real 3D object more cleanly than our everyday intuition ever could. That's why this discovery mattered enough to rewrite crystallography, and why it still matters now. As manufacturing pushes materials into regimes where microstructure and symmetry dominate performance. This is what Future Forge Explored is for, explaining the science before it becomes normal. So subscribe if you want to stay ahead, because we can go even further into the dimension idea, not with mysticism, but with real engineered metamaterials that route waves, steer heat, and make geometry behave like a physical law. The future isn't prediction. It's a design space. And you're watching it expand.